In this work, we consider motion prediction based on neural motion message passing. This is a collaborative work with Dr. Siheng Chen from Mitsubishi Electric Research Lab, Professor Zhang, and Professor Xiao Gu from Shanghai Jiao Tong University. I am Yue Hu from Shanghai Jiao Tong University. Collaborative motion prediction aims to forecast the future motion for multiple interacting actors in the scene. Modeling interactions is essential for motion prediction because interaction empowers actors to cooperate with dynamic environment, and the rich interactions result in complicated motions. Previous works tend to individually study each interaction. However, the interaction associated with the same actor could be dependent. Previous works use simple average or concatenation of actor representations to implicitly model the interactions, which is not expressive and lacks interpretability. In this work, we propose NMMP to jointly and explicitly learn interaction among actors. We construct an interaction graph, use neural motion message passing to propagate contextual information over it, and learn feature representations for both interactions and actors. Our interaction modeling pushes the network to capture and quantify interactions, which would be more effective than previous simple average or concatenation. We designed the motion prediction systems for two settings: the pedestrian motion prediction and the joint pedestrian and vehicle motion prediction. Two frameworks provide distinct wrappers to handle different input formats and characteristics. Both systems share a common pattern. Use an individual branch to model the behavior of a single actor, and an interactive branch to model the interaction between actors. We validate the proposed method in the widely used pedestrian benchmark, SUC, Stanford Zhang, and a reorganized benchmark, NUSINS, for the joint setting. The evaluation matrix are average displacement error and final displacement error. The smaller the better. Here is the comparison with a series of baseline methods. The main information here is that the proposed methods outperform previous SOTAS across various tasks. Here are some visualized motion prediction results. Solid green line is observed ground truth. Dashed green line is predicted ground truth. Blue line is the baseline method social gun. Red line is our proposed method. We can see that our predictions are much closer to the ground truth. Here is a visualization for the learned interaction embeddings. The first column is the visualized interaction embeddings via TS and E. The following two columns are the randomly picked pairs of close interaction samples in the embedding space, colored blue and red. We find that close interaction embeddings in the embedding domain lead to similar trajectory relations between associated actors in the spatial domain, meaning that interaction embeddings reflect interaction types. It also indicates that we can learn interaction embeddings to analyze real-world interaction scenarios. Shown in this page is how the error normalization ratio changed with pedestrian amount in the scene. The x-axis is the total pedestrian amount in the scene. The y-axis is the ADE, colored in red, and FDE, colored in blue, normalization ratio compared with S-scan. We find that the more crowded the scene is, the more gain interaction embedding brings, indicating interaction embeddings capture interactions and help analyze crowded scene. Comparisons with previous SOTAS show that our interaction learning has improvement. The interaction embedding visualization and the error normalization ratio changes further provide interpretability for the interaction learning to some degree. That's all. Thanks for your time.